So we've looked at points of interest of curves, so extrema, local minima, local maxima, global minima, global maxima, and how to use the second derivative in order to calculate the nature of these points. What I'm going to do here is I've got a couple of questions I want you to have a ping at. Read the questions, pause the video, have a crack, come back and see about your solutions. So first one, I want you to take each of the two functions there. I want you to identify their critical points, their endpoints and local extrema, and identify the global maxima and minima where they exist. And then the second question is I want you to use the second derivative to find the nature of all of the turning points of that function there. So pause the video and have a crack at those questions. So the first set of questions here. So I want to identify the critical points, endpoints and local extrema, and the global maxima and minima where they exist. So what I'm going to do in this one here is I'm going to take the derivative. That will help me determine any maxima or minima that exist. I then look at the endpoints of the domain and I take it from there. So if I do f dashed of x, what I end up getting is 2x take away 4, and to get any turning points for that I set it equal to 0. So in order to do that, I have to solve and get x equal to 2. What I can then do is substitute that back into the original equation in order to get what the y part of that coordinate is. So if I substitute it in, I get 2 squared, take away 4 times 2, take away 5. So I get 4, take away 8, take away 5, which ends up giving me -9. So I know a turning point is going to exist at 2, -9. What I can then do is use the second derivative to determine the nature of that turning point. So my second derivative, f dashed of x, is equal to 2. So what that means is at the point here, 2, -9, my second derivative is positive, so the gradient is increasing. So what that means is that that's a minimum point. So I know it's going to be a minimum, whether it's global or local, that all depends. Now for the domain, it's including -2 and 4. So when I calculate those endpoints, I can actually include them in my overall description. So let's look at x is equal to -2. What I then do is I substitute that in and calculate f of -2 to get the y component that goes with it. So if I substitute in -2, I get -2 squared, which is 4, take away 4 times -2, so it's take away -8, which is plus, so I get 4 plus 8, which is 12, take away 5, which is 7. So I know I've got a critical point again at -2, 7. I then look at the 4 as well. So if I have x equal to 4 and I do f of 4, what I end up getting then is I get 4 squared, which is 16, take away 4 times 4, which is 16. So that gives me 0, take away 5, which is -5. So my point there is 4, -5. So they're the 3 big points that are within the domain for that function. What I now have to do is look at them. So this one here, my minimum, is smaller than that one there. So what my curve is roughly going to look like is if imagine there's -2 and there's 4. It's going to start up there. My minimum is going to be down there. And then my endpoint is going to be there. So there's -5 in terms of height, -9 and 7. So I know that this one here, 4, -5, that's going to be an endpoint minimum. I know that this point here, -2, 7, is not only an endpoint maximum, but it is the biggest for the whole thing. So at -2, 7, I know that that is actually going to be a global maximum. And then this point here, at 2, -9, that's a minimum point there. There's no other minimum points within the entire domain, so that there is a global minimum. So there you go, all the critical points identified and their nature. Second one, B, where I've got f of x equals 8x cubed minus 3x to the 4 in the domain -2 to 1. Key thing to note, it's not including 1. We still work with it, but we don't include that in our final overall calculations. First thing, calculate derivative. So I get f dashed of x. In this case, I get 24x squared take away 12x cubed. And I know that that equals 0 for my critical points. So if I then factorise it, I get 12x squared brackets 2 minus x equal to 0. So what that then tells me is that x equals 0 and x equals 2 are critical points on the curve. However, looking at the domain I've got here, -2 to 1, the x equals 2, I don't have to worry about that point, looking at its nature. It is out with my domain. So the only one I need to worry about is x equal to 0. So if I've got x equal to 0 in this case, and I substitute it in, and I do f of 0, well, I get 0. So what that then means is my origin, 0, 0, is going to be some sort of critical point. I then look at the two endpoints, so my -2 and my 1, and see what's going on there. So if I've got x is equal to -2, and I do f of -2, what I end up getting is 8 times the -2 cubed, so -2 cubed is -8, 8 times -8 is -64. I then get 3 times -2 to the 4, so -2 to the power of 4 is 16, so 3 16s are 48, so I get -64 take away 48, that ends up giving me a value of -112. So I know I've got one point there at -2, -112. If I then do f of 1, what I end up getting for that one, something slightly easier, I get 8 take away 3, so I get 5. So what I then know is I've got 3 critical points there within the function that I can look at. And if I imagine sketching the curve, there would be -2, there's my 0, and there would be the 1. So I'd end up starting down here on the -2, I'd go up to 0, and then up to 5 there. Now, what we have to do is look at this point here, and this point here. Now, I think it's fairly safe to say that there, at -2, -112, that point there is an endpoint minimum. And it's safe to say that there's an endpoint minimum. Now the curve is going down the way, can't say it's global, we stick with the endpoint. 0, 0, looking at this point here, the gradient's positive up towards it, and then positive beyond it again. So what that means is it's not turning round at that point. So that there means that is a point of inflection. If we looked at the point here at 1, I could say that is a an endpoint maximum. However, we're not including 1 in the domain, so I can't say anything about that point there itself. So there we go. That's what the behavior of the function looks like in that section that we're looking at there. Second question was use the second derivative to find the nature of all the turning points of this curve here. So first thing we have to do, determine what values of x the turning points occur at, then use our second derivative to calculate its nature. So we take the derivative f dashed of x, what we end up getting is we get x squared minus 3x plus 2. So we've got to set that then equal to 0 and solve it. It's a polynomial, it's a trinomial, so x squared minus 3x plus 2, factorise it to solve, we get x minus 2, x minus 1 equal to 0. So from that, I can say that x is equal to 2 and x is equal to 1. That's where it's going to occur in x. We want the full turning point, so substitute in, and we can get the y part of our coordinates there. So if I substitute in x is equal to 2 in this one, I'd get 2 cubed over 3, so I get 8 over 3, take away 3 times 2 squared over 2, which is the same as 3 times 2, which is 6, plus 2 2's take away 1, so I get minus 6 plus 4, which is -2, take away 1, which is -3, so I end up getting 8 over 3, take away 3, so I end up getting 8 over 3, take away 9 over 3, so I end up getting -1/3. I can then do the second value of x and do the exact same thing for it, substitute it into the original equation. So I'll end up getting 1/3, take away 3 over 2, plus 2, minus 1. So plus 2 minus 1 gives me 1. 1/3 take away 3 over 2, that ends up giving you negative 7 over 6. So I get negative 7 over 6 plus 1, that ends up giving me negative 1/6. So I get 2 turning points, one occurring at 2, negative 1/3, and the second one occurring at 1, negative 1/6. So what I now have to do is determine the nature of both of those points. And to do that, I take the second derivative f double dashed of x. So what I get for that one is I get 2x, take away 3. So for each of these points, substituting the value of x, see what kind of nature I get from it based on the sign of the second derivative. So if I do f double dashed of 2, what I end up getting is 4 take away 3, which is 1. So that's positive. So because it's 1, the gradient is increasing. So I'm able to say that that is a minimum. Then do the second derivative at 1. So f double dashed of 1. I get 2 take away 3. So it's negative 1, which is less than 0. So what that means is that my gradient is slowing down. So my curve is going concave down. So what that means is I'm approaching a maximum at that point. So what I can then say is my point 2, negative 3, that's the minimum turning point. And the 1, negative 1/6, that's a maximum turning point for my curve. Using the second derivative, this makes this a heck of a lot easier and a heck of a lot quicker a calculation for us to be able to do. We have to bear that in mind looking at these sorts of points, and we have to bear it in mind looking at key critical points and extrema of the functions throughout the domain that we're given.